Welcome to Lecture 8, Physical Database Design and Database Infrastructure. Let's learn together in this and see where we can go with the information that had been shared in the previous lectures and in this one. The learning objectives are given here for you to look at, and we'll continue from here. This lecture is a little bit more in depth. We will be describing the problems and techniques for data security, understand the role of database in Sarbanes-Oxley compliance, describe problems and facilities for data recovery, describe database tuning issues, and list areas where changes can be done to tune the databases. Understand impact of cloud-based database services on database infrastructure, and we'll also describe the advantages and disadvantages of cloud-based database infrastructure solutions. So the question comes, what is physical database design? Let's delve into this in a little bit more depth. Physical database design is the process of organizing the logical database design in a way that optimizes performance, storage, and efficiency when implemented in a specific database management system. This involves creating tables, defining indexes, and configuring storage parameters to ensure that the database operates smoothly and meets the application's requirements. One example of physical database design is indexing. Indexes are data structures that improve the speed of data retrieval operations on a database table. For instance, if you have a table of customer records with columns for customer ID, name, and email, creating an index on the customer ID column can significantly speed up the searches for specific customers. This is because the index allows DBMS to quickly locate the desired records without scanning the entire table. Another example is partitioning. Partitioning involves dividing a large table into small, more manageable pieces called partitions. Each partition can be managed and accessed independently. For example, if you have a sales table with millions of records, you can partition it by date so that each partition contains sales data for a specific month or year. This makes an easier understanding to perform operations like backup, archiving, and querying on specific time periods without affecting the entire table. Another example is denormalization. Denormalization is a process intentionally introducing redundancy into the database design to improve performance. For instance, in a normalized database, you might have separate tables for customers and orders with a foreign key linking orders to customers. However, if you frequently need to retrieve customer information along with order details, you might denormalize the database by adding customer information directly to the order table. This reduces the need for joins and can speed up query performance, although it may increase storage requirements and complicate the updates. So the purpose is to translate the logical description of data into the technical specifications for storing and retrieving data. In simple words, the goal is to create a design for storing data that will provide adequate performance and ensure database integrity, security, and recoverability. Information needed for physical design. Normalize relations, including estimates for the range of the numbers of rows in each table. Definitions of each attribute along with physical specifications such as maximum possible length. Descriptions of where and when data are used in various ways, entered, retrieved, deleted, and updated, including typical frequencies of these events. Expectations or requirements for response time and data security, backup, recovery, retention, and integrity. Descriptions of the technologies, database management systems used for implementing database. Critical decisions for physical design. The primary goal of physical database design is data processing efficiency. The organizational role that typically has the primary responsibility for physical database design is called the database administrator, or also known as DBA. So more about database administration will be coming in chapter 12. So choosing the storage format called the data type for each attribute from the logical data model, giving the DBMS guidance regarding how to group attributes from the logical data model into physical records, giving DBMS guidance on how to arrange similarly structured records in secondary memory such as file organizations, selecting structures including indexes and overall database architecture for storing and connecting files to make retrieving related data more efficient, preparing strategies for handling queries against a database that will optimize performance is also known as query optimization. Let's look into an example together. Critical decisions in physical database design also involve optimizing the database for performance, storage, and efficiency, as I discussed earlier. Let's look into a few key decisions. It can be indexing, partitioning, and denormalization, as I discussed earlier. Deciding which columns to index is crucial. Indexes speed up the data retrieval but can slow down the data insertion and updates. For example, if you have a table of a customer orders and columns for order ID, customer ID, and order date, you might choose to index on customer ID column. This makes it faster to find all orders for a customer who specifically you're looking for, which is useful if you frequently run queries to retrieve customer-specific orders. Choosing how to partition large tables can significantly improve performance. Partitioning involves splitting a large table into smaller, more manageable parts. For instance, if you have a table of sales transactions with millions of records, you might partition it by date. Each partition could contain sales data for a specific month or year. This makes it easier to perform operations like backup, archiving, and querying on specific time periods without affecting the entire table. Hopefully this is helpful. Physical design for regulatory compliance. Sarbanes-Oxley Act, also known as SOX, protect investors by improving accuracy and reliability. Committee of Sponsoring Organization is also COSO of the Treadway Commission, IT Infrastructure Library or ITIL, and control objectives for information or related technology, also known as COBIT. Physical database design forms a foundation for compliance with national and international regulations on financial reporting. Without careful physical design, an organization cannot demonstrate that its data are accurate and well protected. The listed, which I just read, are used for full compliance. All data integrity controls must be thoroughly documented and undergo well-documented change protocol procedures. The key focus of SOX or Sarbanes-Oxley Act audits is around three controls: IT change management, logical access to data, and IT operations. Three areas of SOX, as I just mentioned earlier. I'm going to give you a pause here, so read this carefully and we'll continue from there. All right, let's move on. We create usage maps by modifying enhanced entity relationship diagrams to include information regarding sizes of entities, such as numbers of instances, as well as frequencies of the use of these entities. In this way, we come to an understanding of the storage needs as well as the computational demand of the system. Usage analysis should be an ongoing activity. Data volume, here we see an expectation of 3,000 parts subdivided into manufactured and purchased. We also see 150 suppliers, and we see 6,000 associations, each of which describe a particular supplier providing a particular purchased part. Refer to the next slide as a quotation. In essence, you can think of each entity as a table containing the numbers of records or rows, access frequencies per hour. The volume and frequency statistics are generated during the systems analysis phase of the systems development process, when systems analysts are studying current and proposed data, processing, and business activities. The data volume statistics represent the size of the business and should be calculated assuming business growth over a period of at least several years. The access frequencies are estimated from the timing of the events, transaction volumes, and number of concurrent users, and reporting the querying activities. So usage analysis is 14,000 purchase parts accessed per hour, 8,000 supplies accessed from these 14,000 purchased parts accesses, 7,000 suppliers accessed from these 8,000 supplies accesses. Note the access of data from one table may trigger the need for further accesses in other tables. Usage analysis includes providing a representation of this expected flow of access requests. Usage analysis happens where 7,500 suppliers accessed per hour goes to 4,000 supplies accessed from these 7,500 suppliers accesses 4,000 purchased parts accessed from 4,000 supplies. The flow can go in different directions. In the previous slide, the flow was triggered by accesses to parts and flowed through purchased parts, supplies, associations, and finally suppliers. In this slide, we see a flow in the opposite direction triggered by initial access requests for the suppliers. The access request could be queries which retrieve data or updates which manipulate data. Each of these imposes some demand on computing resources, so the type of modeling helps to express that demand. In relational database terms, the word field is a synonymous with column. Fields correspond roughly with attributes in ER and EER models. During conceptual modeling, you identified the attributes for each entity type. During logical design, you converted the entities and attributes of ER model to relations, which are tables, and columns, which are fields. Now, during physical design, you give details of the fields in actuality. Some of these things could be part of logical design. In some respects, logical design and physical design blend together. In other respects, physical design blends with implementation. There are not always hard and fast boundaries between these phases of SDLC. A data type is a detailed coding scheme recognized by a system software such as DBMS for representing organizational data. The data type specifies a bit pattern of data stored in that coding scheme. There are many ways in which data could be physically represented. For the data used in mathematical calculations, numeric fields should be used. For text displays, there are a variety of character-based representations, some of which are fixed length and some of variables length. Other data types include dates, binary representations for images or audio, and even specialized types for XML and other representations. Selecting A data type involves four objectives that will have different relative levels of importance for different applications, represent all possible values, improve data integrity, support all data manipulations, and minimize storage space. Some attributes have a sparse set of values or are so large that given data volumes, considerable storage space will be consumed. A field with a limited number of possible values can be translated into a code that requires less space. A code table would not appear in conceptual or logical model. The code table is a physical construct to achieve data processing performance improvements, not a set of data with business values. So in this case, you probably would not see the product finish table in either the conceptual model or the logical design. In most DBMSs, data integrity controls can be built into the physical structure of the fields and controls enforced by DBMS on those fields. SQL has construct to enforce these rules as we saw in chapter 7. The data types enforces one of the data integrity control because it may limit the type of data, numeric or character, and the length of field value. Other include default values, allowable ranges of values, whether or not values required, null value controls, and enforcing relationships and their cardinality constraints via primary to foreign key matchups. Sarbanes-Oxley Act or SOX legislates the importance of financial data integrity. Controlling data integrity is essential for ensuring that the data stored in a database is accurate, consistent, and reliable. Data integrity involves maintaining the quality and trustworthiness of data throughout its life cycle. This is achieved through various mechanisms such as constraints, validation, rules, and transaction management. One key method for controlling data integrity is the use of constraints. Constraints are rules enforced on the data columns of a table to ensure that data entered is valid. For example, a primary key constraint ensures that each record in the table has a unique identifier, while a foreign key constraint ensures that the values in one table match the values in another table, maintaining referential integrity. Additionally, check constraints can be used to enforce specific business rules, such as ensuring that data column only contains future dates. These constraints help prevent invalid data from being entered into the database, thereby maintaining the data integrity. Of the three, sensitivity testing is the most complex, requiring the most sophisticated programming. This programming can be done within the capabilities of DBMS without requiring external applications to do the programming. Modern DBMS have sophisticated programming capabilities such as case expressions, user-defined functions, and triggers through which complex logic can be performed. It might seem counterintuitive that database designer would want to denormalize a previously normalized, well-structured set of relations after all we spent considerable effort towards conceptual modeling ER, in order to ensure well-structured logical design, and when forced with poorly structured relation we normalize them in our design. Why denormalize now? The answer is performance. When you normalize, you split data into separate tables in order to eliminate or at least reduce data duplication. This helps to ensure that data integrity is achieved, but it comes at a cost. It is much more computationally efficient to query a single table than query multiple tables. So deciding when we denormalize the database can enhance performance by reducing need of complex joins. Denormalization introduces redundancy to speed up data retrieval. For example, in a normalized database, you might have separate tables for customers and orders, with foreign keys linking orders to customers. However, if you frequently need to retrieve customer information along with order details, you might denormalize the database by adding customer information directly to the order table. This reduces the need for joins and can speed up query performance, although it might increase storage requirements and complicate updates. Therefore, it makes sense to, in a controlled way, back off from perfect normalization. In the next few slides, we'll see some of these examples. One-to-one relationships are good candidates for denormalization, such as this example of students with applications. Note that from this diagram, we know that not all students have applications. Question: how do we know this? The answer is the optional on the application side of the submits relationships. Therefore, many students may not have applications, so the application date and qualifications field of the denormalized relation may not be used. This wastes space, but as mentioned earlier, space is cheap these days. Denormalizing is one-to-one case does not, however, threaten data integrity. The question is why? The answer is it is one-to-one relationship, so there won't be multiple records with the same student ID and campus address. Here is the case of many-to-many relationship between vendors and items, which results in three tables or relations. Denormalizing combines the items and price quote tables into a single table called quote. So which attributes will wind up being duplicated in this case? What do you think? The item description, this means that any time of description changes, the changes must be done to all item quotes unless you are willing to tolerate inconsistencies in the item description. So in this case, there is something compromising of data integrity guarantees. Again, we do this for the sake of performance. A query involving two tables is more efficient than a query involving three. Note that composite usage map can illustrate the demand of the extra tables and therefore can be used to justify whether or not denormalization should take place or not. Note that denormalization is most beneficial and least harmful in relations where there is a minimal amount of updates that would occur with the duplicated attributes. In Chapter 9, we will discuss the concept of data warehouses. A data warehouse is generally for the sole purpose of performing complex queries to assist with managerial decisions making. These are never updated except at specified intervals of data integration. Therefore, data warehouses are often non-normalized. You can also have combination of horizontal and vertical. The previous denormalization examples all deal with combining tables to avoid doing joins. Another form of denormalization involves the creation of the more tables by partitioning of relation in multiple physical tables. In other words, we purposely duplicate or copy relations or portions of relations and store these copies in multiple storage locations. As with all physical design decisions, partitioning has its advantages and disadvantages. So you can look at this slide. Advantages of partitioning are efficiency, local optimization, security, recovery and uptime, load balancing. Disadvantages are inconsistent access speed, complexity, and extra space or update time that is needed. We have been talking about relational database structures involving tables, columns, and primary and foreign keys. If this is in fact the way data is actually stored on disk, but it is not. At operating system level, we are always talking about files. Databases are just one of a kind of a file. The tables column key idea is really an abstraction. At lower implementation level, these database files, like all physical files, are actually constructed via different file formats, which will be discussed in the next few slides. Most database management systems store many different kinds of data in one operating system file. By operating system file, we mean a named file that would appear on disk directory listing, such as a listing of the files in a folder on a C drive or on your laptop drive of your local or personal computer. A file organization is a technique for physically arranging the records of a file or secondary storage device. Typical file organizations include sequential, indexed, and hashed, which we will see in the next few slides. Another possibility is something called a heap, but this has no order and is not ideal for quick access. Imagine a telephone book where people were in a particular order. You would potentially have to search through each and every name, therefore finding what you need. The other file organizations are designed to bring quick access and or optimize insertion, modification, and removal of the items. With modern relational DBMSs, you don't need to design file organizations, but you may be allowed to select an organization and its parameters for a table or physical file. So here are a few factors to consider. It's like fast data retrieval and throughput, efficient storage, space utilization, protection from failure and data loss, minimizing need for reorganization, accommodating growth, security from unauthorized use. Okay, let's continue. In essence, when data is arranged sequentially, you can cut the search space in half each time you look. For example, suppose you wanted to find the flyers. First, look at the middle item. The list, suppose it is whose years. Since flyers come before whose years, you know it has to be the group before whose years. So, then look at the middle of that group. Suppose this item was devils. At this point, you know it has to be between devils and whose years. So, the speed of accessing a desired record, knowing the primary key in a sequential file, is much, much faster than accessing it in unordered file, or also known as heap. But sequential file organization always requires data to be sorted. Therefore, such a file must be resorted every time new items are inserted. So if any existing items are changed, so the speed of access comes with a significant maintenance cost. In an indexed file organization, the records are stored either sequentially or non-sequentially, and an index is created that allows the application software to locate individual records, like a card catalog in a library. An index is a table that is used to determine in a file the location of records that satisfy some condition. Each index entry matches a key value with one or more records. An index can point to unique records. A primary key index, such as on the product ID field of a product record, or potentially more than one record. An index that allows each entry to point to more than one record is called secondary key index. An advantage of the indexed file organization over the sequential is that it is easier to insert and delete data. Because the index is composed of many smaller lists of actual data items seen in the bottom of the tree, then sorting an individual cluster is much less costly than sorting a whole file. Also, if you keep the individual lists small enough, then even if they are unsorted, the search time is not so bad. The trick is indexing and specifically keeping an optimal number of levels within the index. In this case, we see two levels of indexing, below which are the sublists of data items. The index organization in this figure splits the top level into three groups. Any team name starting with A to F goes in the first group, and G to P in the second, and Q to Z in the third. Within each group, there are second split into three subgroups each. Index file organization is often used with attributes that are likely to be frequently used in queries. Part of the physical design process involves choosing which columns of a table to index, as we will see later. A hashing algorithm is a routine that converts a primary key value into record address or record address. Although there are several variations of hash files, in most cases the records are located non-sequentially as dictated by the hashing algorithm. Thus, sequential data processing is impractical. A typical hashing algorithm uses a technique of dividing each primary key value by a suitable prime number and then using the remainder of the division as the relative storage location. For example, suppose that an organization has a set of approximately 1,000 employees' records to be stored on magnetic disk. A suitable prime number would be 997 because it is close to 1,000. However, consider the record for employee ID 12396. When we divide the number by 997, the remainder is 432. Thus, the record is stored at location 432 in the file. Hashing algorithm could potentially map two different primary keys to the same location. If that happens, there will be a list at that location similar to the lists in the index file organization described earlier. Clustering records is best used when the records are fairly static, as in a data warehouse. When records are frequently added, deleted, and changed, wasted space can arise. It may be difficult to locate related records close to one another after the initial loading of records, which defines the clusters. Clustering is, however, one option in a file design. Designer has to improve the performance of tables that are frequently used together in the same queries and records and reports. So clustering and join indexes are both done for the purpose of optimizing join queries. Part of the physical design process is to decide which fields need indexing. Primary keys are normally indexed by default. The database designer typically chooses which other fields to index based on expected usage of those fields. In queries and inserts, if the fields are used a lot as condition of inquiries, this increases the importance of indexing, but indexing comes at a cost, which involves maintaining the index. Indexes are costly for fields that get updated a lot. So when to use indexes? Use on larger tables. Index a primary key on each table. Index search fields where fields frequently in where clause, fields in SQL order by and group by commands when there are greater than 100 values, but not when there is less than 30 values. So you avoid using indexes for fields with long values, perhaps compress values first. If key to index is used to determine location of record, use surrogate like sequence number to allow even spread in the storage area. DBMS may have limit one on number of indexes per tables and number of bytes per indexed fields. Be careful of indexing attributes with null values. Many DBMSs will not recognize null values in an index search. Use a query optimizer always. Clustering records is best used when the records are fairly static, as in the data warehouse. When records are frequently added, deleted, and changed, wasted space can arise, and it may be difficult to locate related records close to one another. After the initial loading of records, which defines the clusters, clustering is, however, one option a file designer has to improve the performance of tables that are frequently used together in the same queries and reports. So clustering and join indexes are both done for the purpose of optimizing join queries. Let's look into this using library as the example. Imagine you are the librarian at your department library. You have a huge collection of books and you need to organize them in a way that makes it easy to find what you need quickly. So if we look at clustering, one day you decide to organize the books by genre. You create separate sections for fiction, non-fiction, science, history, and so on. Within each section, you arrange the books alphabetically by the author's last name. This way, when someone comes in looking for a specific type of book, they can go directly to the relevant section and find it quickly. This is similar to clustering in databases. Clustering involves grouping related data together physically on the disk. For example, if you have a database of books, you might cluster the books by genre. This means that all the fiction books are stored together, all the science books are stored together, and so on. When you need to find the specific book, the database can quickly locate the relevant cluster and retrieve the information faster. Whereas join indexes, let's take this in the same librarian aspect. Now let's say you also keep a separate list of all the students who have borrowed the books, along with the titles they borrowed. This list is like the join table that connects students with books. However, every time someone asks you which students have borrowed a specific book, you have to look up at the book and in the book section, then cross-reference it with student list. This can be time consuming. To make this process faster, you create an index card for each book that lists all the students who have borrowed it. This way, when someone asks for the students who borrowed the particular book, you can just grab the index card for the book and quickly provide that information. This is similar to join index in the databases. A join index is a special type of index that speeds up the process of joining two tables. For example, if you have a table of books and a table of students who borrowed those books, a join index would pre-compute the join between these two tables. This means that when you need to find out which students borrowed a specific book, the database can quickly look up the join index instead of performing a time-consuming join operation every time. So by using the clustering and join indexes, you make the library or the database much more efficient and user-friendly. Now let's look into The same way as I discussed a library example by making you the librarian, how and why query optimization is important. Imagine you are a doctor at a hospital. Every day you need to access patients' records to make informed decisions about their treatment. The hospital uses a sophisticated database to store all patient information, including medical history, test results, and appointment schedules. So, what is the problem here? One day you notice that it takes an unusually long time to retrieve patient records. You ask the hospital's IT specialist, let's say that person's name is Alex, to look into the issue. Alex discovers that the database is running the complex query to fetch patient records, but this query is not optimized. It is like asking a librarian to find a specific book by searching every shelf in the library instead of using catalog. So, how query optimization is done? Alex decide to optimize the query. Query optimization is like giving the librarian a better way to find the book. Instead of searching every shelf, the librarian uses the catalog to quickly locate the book. In the context of hospital database, Alex rewrites the query to make it more efficient. First, Alex identifies each parts of the query are taking the most time. So which parts of the query are taking the most time? For example, the query might be searching through every patient record to find those with specific condition. Alex adds an index on the condition column, which is like creating a catalog entry for the book about that condition. Now the database can quickly find patients with the condition without scanning every record. Next, Alex looks at how the query joins different tables. The original query might join the patient table with the test results table and the appointment table in a way that is insufficient. Alex writes the query to join these tables in a more logical order, reducing the amount of data the database needs to process. Finally, Alex checks for an unnecessary operation in the query. For example, the query might be sorting the results in a way that is not needed for the doctor's use case. Alex removes this sorting operation, further speeding up the query. After Alex optimizes the query, you notice that a significant improvement in the time it takes to retrieve patients' records. What used to take minutes now takes seconds. This allows you to make quicker and more informed decisions about patient care, ultimately improving the quality of treatment. So, why query optimization is important? It is crucial because it ensures that the database performs efficiently in the healthcare system. This efficiency can mean the difference between life and death. Doctors need quick access to patients' information to make timely decisions. An optimized query means faster data retrieval, which leads to better patient care and more efficient health care system. Data dictionaries and repositories. Data dictionary is documents, data, elements of a database. System catalog, system created database that describes all database objects. And information repository stores metadata describing data and data processing resources. Information model is a schema of the repository information. Repository engine is software that manages the repository objects. Repository database is where the repository objects are stored. Everything has an architecture include metadata management. Database administrators and data warehouse repositories use repository engine tools to administer the organization's metadata. All of these are DBMS features, enable a DBA to implement data security in an organization's database. We'll discuss these in next few slides. So views or subschemas, integrity controls, authorization rules, user-defined procedures, encryption, authentication schemas, backup, journalizing, and checkpointing. So we discussed the views in chapter 6. We can set access privileges on these views to control which users get to see which aspects of the database. As you can see, the integrity controls discussed in chapter 4 also serve a security purpose. Authorization rules grant subjects access to objects, specifying which actions and constraints govern the subject's access. Subjects are users or groups of users. Objects are entities in the database. Actions are the types of DML or data manipulation language commands permitted for the given subject on a given object. The commands could be select, insert, update, delete, and these actions can be further constrained based on the authorization rule. All of these are available to our DBA or database administrator to control via the DBMS software. So here we see these rules expressed as an authorization matrix, the figure 8.9, and hopefully this is helpful. These authorization tables are simplified representations of authorization rules. One is for subjects and the other is for objects. The key idea is in both authorization matrices and authorization tables is that you are controlling who gets what kind of access to which data elements. Privileges are granted for different database activities: select, insert, update, delete, alter, index references, and procedure function execution. Some DBMS products include encryption routines that automatically encode sensitive data when they are stored or transmitted over communication channels. For example, encryption is commonly used in electronic funds transfer or EFT systems. Other DBMS products provide access that allow users to code their own encryption routines. Authentication is not the same as authorization. Authorization rules specify who has what access rights to what data elements. Authentication schemes are means of ensuring that a user is who he or she claims to be. Obviously, passwords are the first line of defense, but these are imperfect. It is hard to remember multiple complex passwords. So people tend to simplify them or worse, write them down. Smart cards, biometrics, and combination of some current means of improving authentication we can see in this slide. Sometimes data is lost or damaged. So DBMSs include facilities for recovering from the lost. Generally, this involves backing data up and allowing it to be restored. We'll talk more about mechanics of backup and recovery shortly. Actually, the recovery process requires both backup snapshot and change log, as we'll see shortly. Imagine that a database was last backed up on Sunday at midnight. This means that we need all transactions and change log entries since Sunday at midnight in order to bring it up to date. We start with the backup and then repeat the database changes. Note that difference between the transaction log and database change log. Transaction logs are used from one form of recovery, restore or rerun, and database change logs are used for another, forward recovery. The databases need to be in the quiet state in order for backup to occur. A DBMS may perform checkpoints automatically, which is preferred, or in response to commands in user application programs. Checkpoints should be taken frequently, say several times an hour. So why recovery manager is important? Let's look at this in a story way. Okay, ready for the story? Imagine you are a manager at a large factory or gigafactory that produces high quality widgets. The factory relies heavily on a sophisticated database system to track inventory, manage orders, and coordinate production schedules. Every day, hundreds of transactions are processed, from receiving raw materials to shipping finished products. So, what is the problem here then? One day, a sudden power outage hits the factory. When the power comes back on, you realize that the database system has crashed. This is a major problem because the database contains critical information about ongoing orders, inventory levels, and production schedules. Without this information, the factory can't operate efficiently and you risk missing important deadlines. So the recovery manager we use here to rescue this issue or resolve this problem. So fortunately, your database system has a built-in recovery manager which acts like the factory's emergency response team. The recovery manager is designed to handle exactly this kind of situation and restore the database to a consistent state. So here's how it works. Let's take logging as the first example. Throughout the day, the recovery manager keeps a detailed log of every transaction that occurs in the database. This log records every change from updating inventory levels to processing new orders. When the power outage happens, the log stops recording, but it has complete history up to the point. Checkpoints is your second recovery manager main function. The recovery manager also periodically creates checkpoints, which are like snapshots of the databases at specific times. These checkpoints provide a known good state from which the recovery process can start. Think of them as saved progress with the points in a video game. If something goes wrong, you can go back to the last checkpoint. Last not the least, rolling back or roll back and roll forward. When the power comes back, Recovery Manager springs into action. It uses log to determine which transactions were in progress when the crash occurred. It then rolls back or undo any incomplete transaction to ensure that the database is not left in a half-finished state. Next, it rolls forward, redos any completed transactions that were not yet written to the database, ensuring that all the work done before the crash is accounted for. So, in this case, the recovery manager is a hero. The database is quickly restored to a consistent state. Orders that were in progress are either completed or marked incomplete. Inventory levels are accurate and production schedules are up to date. The factory can resume operations with minimal disruptions, ensuring that deadlines are met and customers are satisfied. Why it matters. The recovery manager is crucial for the factory's operations because it ensures data integrity and business continuity. Without it, a power outage or other failure could lead to lost data, incorrect inventory levels, and missed deadlines. This could result in financial losses, damaged reputation, and unhappy customers. So, Recovery Manager in a database is like the emergency response team in the factory. It ensures the database can quickly recover from failures, maintaining data integrity, business continuity, and overall efficiency. Rollback is the backout or undo of unwanted changes to the database, as I discussed earlier. Before images of the records that have been changed are applied to the database and the database is returned to an earlier state. Rollback is used to reverse the changes made by transactions that had been aborted or terminated abnormally, so as we just discussed. And roll forward is a technique that starts with an earlier copy of the database. After the images, the results of a good transaction are applied to the database. As I discussed earlier, however, this is a good pictorial representation for you to look at this. This approach is an alternative to restore or return or rerun. It is much faster and does not require the use of transaction log and repetition of transactions. Instead, It makes use of database change log. Of course, this requires more upfront activity, maintaining the database change log in addition to the transaction log. But actual recovery itself, if needed, runs much faster with more accuracy. In the next slide, we see some types of failures and the best recovery techniques to use. Notice that reprocessing transactions is never preferred option. Notice also that all these are possible because of disk mirroring, backups, and the maintenance of transaction and database change logs. All of these are techniques to make the database fault tolerant. So system failure, as I just discussed, and database destruction. Switch to duplicate database. You can have in the data warehouse already a backed up database that you can use. Disaster recovery is by itself is a humongous field. So develops a detailed written disaster recovery plan. You have to do that and test this regularly. Choose and train a multidisciplinary team to carry out the plan. Establish a backup data center at an off-site location located a sufficient distance from the primary site. Send backup copies to databases to the backup data center on the scheduled basis. Cloud-based data management services. Cloud computing is a provisioning or acquiring computing services on demand using centralized resources accessed through the public internet or private networks. Infrastructure as a service is another area where cloud service involving hardware and various types of system software resources. Platform as a service is where cloud service involving hardware and various types of systems software uses. You might have heard of GCP, Google Cloud Platform. You might have heard of AWS, Amazon Web Services, or Microsoft Azure. They all are cloud-based data management services in major. So again, let's continue. Software as a service, you might have heard that DBAS or database as a service. They are all services which are available when you work with the cloud. Benefits of cloud data management services. So let's look at this in a little bit more depth with an example. So let's meet Sarah, the manager of a very busy call center that handles customer support for a large e-commerce company. The call center is the lifeline of the company, handling thousands of customers' inquiries every day. Initially, the call center used an on-premise or on-the-premises database system to manage customer data, call logs, and support tickets. However, as the company grew, Sarah began to notice several challenges with this setup. The on-premises system struggled to keep up with the increasing volume of the calls and data, making it difficult to scale efficiently. Additionally, maintaining the system required a dedicated IT team to handle backups, updates, and security patches, which was costly and time-consuming. Recovering from hardware failure or natural disaster was a slow and complex process. The agents could only access the database from their office computers, limiting their ability to work remotely or respond to urgent issues outside the office hours. To address these challenges, Sarah decided to migrate the call center's data management to a cloud-based solution. The cloud provider offered a scalable, secure, and accessible platform that promised to address all the issues they were facing. With the cloud-based systems, Sarah could easily scale the resources up or down based on the demand, ensuring that the call center could handle peak seasons without downtime. The cloud provider handled all the maintenance tasks, freeing up Sarah's IT team to focus on other critical tasks like improving customer support tools, analyzing data to enhance service quality. The cloud-based system also offered robust disaster recovery features, automatically backing up the data to multiple locations to ensure it was always available, even in case of major disaster. Additionally, the cloud platform provided advanced query optimization techniques such as clustering and join indexes, which significantly improved the speed and efficiency of data retrieval. This allowed call center agents to quickly access customer information and resolve issues faster, enhancing customer satisfaction. After migrating the cloud based data management systems, Sarah noticed a significant improvement in the call center's efficiency and customer satisfaction. Agents could handle more calls with better accuracy thanks to the scalable and accessible platform. The reduced maintenance burden allowed the IT team to focus on innovations that further improved customer support. Moreover, the call center was now better prepared for any unexpected events, whether it was sudden surge in calls or a natural disaster. The cloud-based systems ensured that customer data was always available and secure. The benefits of cloud-based data management were clear. The call center could now provide faster, more reliable, and more flexible customer support, leading to happier customers, better reviews, and increased loyalty. This is not only improving of the customer satisfaction but also contributing to the company's overall success. Downside of cloud-based data management services: existing systems do not yet provide capacity using a model that would automatically adapt to the changing requirements targeting the system. So you have to non-stop using the agile or scrum methodology create these systems appropriately. Current systems are not providing full consistency guarantees in the highly distributed environment. That is also needed to be taken care by the DBAs, so the data is appropriately stored and committed and is consistently available. So live migration is still a challenging task that requires manual planning, initiation, and management. It is challenging to be able to monitor the extent to which cloud providers are maintaining their service level agreements, or also known as SLA commitments. The DBAS, or database as a service solutions, are still struggling to find fully scalable models to provide ACID, atomicity, consistency, isolation, and durability support for the transactions. However, big data has changed a lot. MongoDB, Cassandra, HBase has been new players in this. So hopefully this has given you some decent thoughts to ponder. So happy learning. Let's take a break of 5 to 10 minutes. Let's come back within 7 to 10 minutes time frame.